All right, 7.4. We're going to spend quite a bit of time on this, and I'm going to go over it here on the videos, but I'm also going to talk about it again. I'm going to kind of do another lecture of this in class just to make sure that you understand this. Okay, and it is nucleophilic substitution reactions. Okay, basically the reaction is very straightforward. You are going to substitute your halogen for a nucleophile. Okay, remember nucleophiles have negative charges. And it's a very simple reaction. You're just substituting whatever your halogen is, bromine, chlorine, iodine, for whatever your nucleophile is. That's it. So this is going to substitute for this. Okay? So that is the substitution reaction. The second reaction we're going to talk about, which is in a different section, is elimination reaction. And that's, instead of it substituting, what it's going to do is actually going to pluck off this hydrogen here. These electrons in this bond are going to pop down to form a double bond and kick out your bromine. So you form an alkene. You eliminate the hydrogen and the bromine. Okay? But for this section, we're going to talk about the substitution reaction. And there are two different mechanisms that we're going to talk about. The mechanisms are an SN2 mechanism, which we're going to talk about first, and an SN1. Okay? The S stands for substitution. The N stands for nucleophilic. The 2 stands for a bimolecular reaction. This is the 2 is a bimolecular, happens to do with the kinetics of the reaction, and the 1 here stands for unimolecular. Now, some of you have taken Chem 112 where you've talked about kinetics. We're not going to nearly get into the mathematics that they got into that class. It's just more of an understanding of what's going on. Okay, so let's talk about the nucleophilic reaction. There's a lot of information on these slides. I'm going to try to go through them pretty slowly, but like I said, I'm going to go over it again in class so that we have a really good understanding of this. Okay, regardless of the mechanism, okay, regardless of the fact it's an SN1 or an SN2, it doesn't matter. The overall changes during a nucleophilic reaction are the same. Okay, the change is the nucleophile substitutes for your halogen. Okay. And it substitutes for your leaving group, which is a halogen, and you yield a new product. Okay. Now, this example here is showing what an SN2 reaction looks like. This is showing what an SN1 reaction looks like. All right. And the main difference between the two is this is a very strong nucleophile. See how it says a negatively charged nucleophile? That's considered strong. Anytime you have a negative charge, it's considered a strong nucleophile. This is neutral. Okay, there is no negative charge. But it has lone pairs. Okay, so it does have lone pairs, but it has a neutral charge. That's what's called a weak nucleophile. That's the difference. The big difference between the mechanism of SN2 and SN1. The other one is our substitution on our R group. Is it a primary alkyl halide? Is it a secondary alkyl halide, or is it a tertiary alkyl halide? Depending on what type it is, will also again depend on if it's a primary, an SN1 or an SN2. Okay, so that is a difference. Okay, but the overall reaction is the same. You still get a nucleophile. Now, you might not always get a plus charge here, so they do show you a plus charge. You might not always get this plus charge, but they're just trying to show you that if you're neutral and you now share your bonds, you're going to get a plus charge. Okay, but this is the main difference: strong nucleophile versus a weak nucleophile. Okay, so this is a page just to kind of show you some of the common nucleophiles that we use. Okay, so water is a good example. Now think about it: is water a weak nucleophile or a strong nucleophile, based on what we just talked about? Weak or strong? Remember, strong means it has what charge? A negative charge. Is there a negative charge here? No. Therefore, this is going to be a weak nucleophile. Okay? This has a negative charge. This would be a little bit close on the strong side. All right? This does have resonance, so it weakens it a little bit, but I consider it strong. This would also be a weak. Okay? All the ones that have a negative charge, these I consider strong. Okay, so how do you know the difference between strong and weak? I just told you, it has a negative charge. And then the weak version, the weak form. So how do I know if it's the strong form or the weak form? Okay, well, let's say I have a hydroxide up here. Okay, that's the strong form. If I protonate the strong form, So let's write it like this. If I put a proton in place of it, it becomes weak. So that's all the differences between a strong nucleophile and a weak nucleophile. So if I have CH3O-, that's the strong form. What would the weak form be? If you said CH3OH, you'd be correct. So it's just putting an H in place of that negative makes it from a strong to a weak. An H can't be a carbon, can't be anything else. It has to be the hydrogen form of it. So that's it. Okay, that's how you tell if you have a strong nucleophile or a weak nucleophile, by if you have a negative charge or if you have the hydrogen in place of the negative charge. Okay, so let's talk about SN2 reactions. Okay, the first thing I want to mention, I'm going to start at the bottom. I know it's kind of weird. I just took the slides from the publisher. If I read them more closely, I would have changed them. But the first thing is you need a strong nucleophile, negatively charged nucleophile. It's got to be strong. Okay, that's the key thing. Okay. The other thing about the mechanism is that the reaction is with inversion at the reacting center. We will talk about this. This is just kind of a cheat sheet of everything on there. It takes place in a single step. Okay. So it's what's called a concerted mechanism. Concerted mechanism. It happens all at once. There are no intermediates, so this is kind of combined. There are no intermediates. The entering nucleophile is 180 degrees from the leaving group. So again, these kind of tie together. We will talk about it once we get to it, and then we will go back to a slide like this and review. It's a bimolecular reaction. We will talk about the rate in a second, but bimolecular, that's why you have a 2 here. And the rate of reaction depends on the concentration of both the nucleophile and the substrate. So the way that you write a rate equation is the rate is equal to a constant. There's some constant. It doesn't matter what the constant is. And it's the concentration of the nucleophile times the concentration of the electrophile. Okay, so if I raise the concentration of the nucleophile, I raise the rate. If I raise the concentration of the electrophile, I raise the rate. If I double this and I double that, the rate is 4 times as fast. Okay, so that's what's meant by the rate. So let's look at examples where all this is tied together. Okay, so here's a perfect example. The reaction involves a transition state in which both reactants are together. So this is the concerted part of the mechanism. Okay, so notice my nucleophile. Here's my nucleophile, the hydroxide. Okay, here is the halogen. Okay, the negative is attacking my partial positive carbon. Okay, now it's concerted, meaning it happens all at the same time. As my OH is attacking the carbon, the bromine is leaving at the same time. Okay, the difference is in the SN1 process, the leaving group leaves first, then your nucleophile attacks. In this case, as the nucleophile is attacking, the leaving group is leaving. Also, this bromine is very, very large. Okay, imagine the bromine, you know, like that big. Okay, this nucleophile can't squeeze in on this way or anywhere. It has to come in exact 180 degrees from the alkyl halide. It's what's called a backside attack. Okay, it's coming from the backside, and you have what's called inversion of configuration, because what happens is as this is coming in, it pushes these 3 groups out of the way. So it pushes the methyl group, the hydrogen, the ethyl group. It pushes these out of the way. So you can kind of see how these groups are kind of facing left, and now they're kind of in the plane as the OH is coming, and then as the OH starts bonding and the bromine leaves, notice how it's kind of flipped the opposite way. Okay, so it's kind of like an umbrella. I kind of think of it as an umbrella effect. So imagine you have an umbrella and you're in a storm and it's windy outside, and what happens? It comes in and flips your umbrella inside out. That's kind of what's happening. As the OH is coming in, it flips these the other way, and your OH is now bonded on the other side. Now you can't see this. Let me actually drag the video. There you go. So you can see the name of it. Notice we're starting with the S enantiomer, and we are now ending with the R enantiomer. So we have inversion. Right, inversion of configuration. That's what an SN2 reaction does. You will get 100% inversion. Okay, there's also some notes in here that talk about the stereochemistry is inverted as the COH bond forms fully and the bromide ion departs with the electron pair from the former C bromine bond. Okay, so in SN2, notice also, which we'll talk about pretty much in a few slides, this is a secondary alkyl halide. Secondary because it's attached to 2 carbons. Okay, one of the things about SN2s is we do not want this too hindered. If it's too hindered, then the nucleophile is going to have a hard time squeezing in here. Okay, so we're going to see this in probably the next slide or few. But the important thing I want to get at is that the nucleophile comes in exact opposite of the bromine. Okay, 180 degrees. And because of that, it has this. It's all happening. It's all concerted, and because of that, it has inversion of configuration. Okay. So again, here's another example of the transition state of an SN2 reaction. Has roughly a planar arrangement. Notice, you see how this is kind of planar now? It goes from a tetrahedral kind of structure, and now this stuff right here is all planar. Okay, you can kind of see it a little better right there. Okay, which causes the inversion. So the steric effects, this is what I was talking about, the steric effects. Okay, here they kind of show a primary. So this is actually a methyl alkyl halide. So this is a methyl alkyl halide because it's a carbon with 3 hydrogens. The smallest groups you can get. Now imagine a nucleophile coming in right here. Okay, you have these 3 little hydrogens. Nucleophile can easily see this carbon. Okay, now let's put on a methyl group. Okay, right here is the methyl group. Okay, well, here's the carbon I'm trying to attack. I can, okay, if I have a nucleophile, I can kind of see it still. I can still kind of share. Okay, this is a primary alkyl halide. Let's now look at a secondary. Why is it primary? Because this carbon is attached to 1 carbon. This carbon is now attached to 2 carbons, so secondary. Okay, right here you can still kind of see that carbon, right? So my nucleophile can kind of squeeze in here still, a little bit harder, okay, but it can probably still do it. Now we get to tertiary. I can't even see. That carbon that's attached to this bromine is so buried in here, this nucleophile can't even attack. Okay, this is a tertiary. So at this point, when you get more substituted, the reaction slows down. Okay, so as far as your rate of reaction, methyls go the fastest, followed by a primary, followed by a secondary. Tertiaries don't even go. If you have a tertiary alkyl halide, there's no way you are squeezing that nucleophile in there. No possible way. Okay, so it kind of just shows you the carbon atom in A, all right, is readily accessible for a fast SN2. Okay, the primary and the secondaries and the tertiaries are successively more hindered, resulting in successively slower SN2 reactions. Okay, so this is kind of a summary. The order of reactivity in SN2s, the more alkyl groups connected to the reacting carbon, the slower the reaction. Okay, so notice methyl 2 million times faster than if you have, this is still a primary. Okay, it's still primary because it's attached to 1, but notice the primary is attached to 3 other carbons. So this kind of shows you, hey, even if this is primary, it still really depends on the steric effects of all the other groups around it. Okay, but a primary goes pretty fast, a secondary is okay. Again, primary with gigantic groups kind of slows things down, but now you have a tertiary, there's no way that that reaction is going that fast. Okay, and the leaving group is the next thing I want to talk about. And the leaving groups, we're not going to talk about this OTS. Let's just kind of ignore that. That's not something we talk about in this class. But iodine goes faster than bromine, goes faster than chlorine, goes faster than fluorine. So pretty much it's the halogens. Okay, I've always told you that fluorine, don't even worry about fluorine. So you really want a chlorine, a bromine, and an iodine on there, and you will have a very fast reaction.